Okay, up on the board we have the learning target. Okay, we're talking about the ideal gas law. So our learning target is to understand the relationship between pressure, volume, mass, and temperature of a gas. And also to perform calculations using the ideal gas law equation. As we're going to see here coming up, the ideal gas law equation is a combination of three different laws. Okay? Three different laws put together, and it's dealing with how the pressure, the volume, the temperature, and the number of moles of a gas relate. Okay? So these have to be of gases. So in order to do these two learning targets, we have certain success criteria. The first one is to be able to state and recognize the ideal gas law and know the value in units for the ideal gas constant. I'm going to give you four. I'm going to give you four different ideal gas constants that we could possibly be using. The second of the success criteria is given three of the four values, PV, N, RT, pressure, volume, moles, or temperature. We can use the ideal gas law to calculate the fourth value. Okay? So we're going to have five things, one of which is going to be R, which is the gas constant. If we have four out of those five things, we can calculate the fifth. So that is what we are going to be doing. It sounds a lot harder than what it actually is, I think. And finally, we are going to use measurements of mass, volume, density, pressure, and temperature of a gas to calculate the molecular weight. So basically, we're going to use all of these things with a different equation to calculate the molar mass. So we're going to learn two equations today that we're going to manipulate to make some calculations. Now, I told you that the ideal gas law equation came from three different simpler laws, and those are Boyle's law, Charles' law, and Avogadro's law that we have listed right there. Now, let's look at Boyle's law, first of all. Boyle's law was dealing with volume and pressure. So he said that if I have a constant number of moles and a constant temperature, then volume is inversely proportional to pressure. Now, if something is inversely proportional, as one gets bigger, as one goes up, the other one gets smaller or goes down. And inversely proportional, you see how that P right there is in the denominator. Okay? So that means it's inversely proportional. So stop and think. If I had a balloon, okay, and my balloon wasn't totally filled with air, it had room to move. Okay? If I had a balloon that had a certain amount of air in it, okay, it's going to be at a constant temperature. It's going to have a certain amount of moles inside it. If I would take and I would squeeze that balloon, if I would apply pressure to it, what would happen to the volume? It would go down, wouldn't it? Okay, if I squeezed it together, it would go down. If I would let up on the pressure and make it less, it would get bigger. Okay, so that's the whole idea there. The inversely proportional. As the pressure increases, the volume decreases and vice versa. As the volume would increase, the pressure would be decreasing. Charles' law is the second one of the simpler ones. And Charles said that if I have a constant number of moles at the same pressure, that the volume and the temperature are directly proportional. So if the volume goes up, the temperature goes up. If the volume goes down, the temperature goes down. Now, Charles' law here, when I think about this, let's say that I've got a bottle, a plastic bottle of pop that's empty that I just threw in my car. Okay? Anybody ever do that? I personally don't do that. But if you got an empty bottle of, I don't know, it used to be Mountain Dew, now there's nothing in it. Okay? Just sitting in your car with the cap on. Now, you've got a certain amount of moles, and you've got a certain pressure. Okay? At night, what happens to the temperature? Tends to go down. So have you ever walked in and that bottle been real flimsy? That's because the temperature went down and the volume went down. If you bring that inside and set it down and the temperature increases, what's going to happen to the volume? It's going to go up too. So that will expand a little bit. Okay? That's Charles' law. The final one is Avogadro's law, our good buddy Emilio. Now, he said that if I have a constant pressure and a constant temperature, that if I increase the number of moles, what's going to happen to the volume? It's going to go up. Okay? It's going to go up. Doesn't that make sense? Okay? We've related moles to mass, right? If I increase the mass of something, which increases the moles of something, doesn't that make sense that it's going to make more of a volume? Sure. Okay. Now, when we put these three simpler laws together, and I'm not so worried about doing all this stuff, okay, when we put the simpler laws together and we add the gas constant, which is R, we add the gas constant, then we come up with the ideal gas law equation, which is PV equals nRT. The pressure times the volume is equal to the number of moles, the gas constant, and the temperature, all multiplied together. So that is our ideal gas law. Now, what I want you to do is, here are 4 different gas constants that you don't have in your notes. You need to write these down and make sure that you have the labels listed correctly. Now, with these values for the ideal gas law constants, notice up here what I have in red. Of the labels, okay, L is liters, K is temperature in Kelvin, mole is obviously the number of moles. So the red label here is the pressure. Excuse me. So when we have pressure in atmospheres, okay, we use a certain ideal gas constant. When we have pressure in kilopascals, which is this kPa right there, kilopascals, millimeters of mercury, torr, those are all different labels that can be used for pressure. So one of the things we're going to need to do is determine which one of these ideal gas law constants that we need to use. Okay? Most of the time, we're going to be using one of these 2 values. Okay? This value down here, I know that we'll use for a lab. I know that we'll use that value for a lab coming up probably next week. All right? So those are different constants that we have. Now, our second equation, okay, our second equation that we're going to use is dealing with density, okay, dealing with density. And right here is that equation, and the way I remember it is PM, post-mortem, you're covered with dirt, okay? Post-mortem, after death, you're covered with dirt. So PM equals dirt is how I remember this particular equation. Now, we know P is pressure. M is the molar mass. D is the density. R is the constant. T is the temperature. Okay? So it's just a little bit of a variation from PV equals nRT. Okay? This is PM equals dirt. So those are the two equations that we're going to need to do these ideal gas law calculations. So what I would like for you to do is, here is our very first practice problem that we will be working. Copy that down into your notes, and then I will work this for you. All right, the question states that if I have 7.7 moles of a gas at a pressure of 0.09 atmospheres and at a temperature of 56 degrees Celsius, what is the volume of the container that the gas is in? So I can get a couple of things from this before I even start to do my calculation. I can see right here that I have atmospheres. So I am going to be using this particular value for R. 0.0821 liters times atmospheres all over Kelvin times mole. Now notice it says that we're in Kelvin. So I am going to have to convert my Celsius into Kelvin. Now, when I do these particular problems, okay, I just simply line up on the side P, V, N, R, T, because I need to have 4 out of those 5 values to be able to do one of these calculations. Well, I know that I have R, because I just said that my R is 0.0821 liters times atmospheres all over Kelvin times mole. That label will help me cancel labels when I work the problem. Do I have a pressure? Absolutely. 0.09 atmospheres. Do I have a volume? That is what I'm trying to calculate, my volume. Do I have a number of moles? Yes, I do, 7.7 moles. Do I have a temperature? Yes, I do, 56 degrees Celsius. Now, why do I want Kelvin instead of Celsius? We don't have negative values on the Kelvin scale, okay? I don't want those negative values. So, do you remember, anybody remember what our conversion factor is for Kelvin? Kara? 273.15, I heard you say, right? Okay. So when I do that conversion, I come up with 329.15 Kelvin. Remember, Kelvin is not degrees Kelvin, it's just Kelvin. So, I've got this right here. I've got all the data that I need. Now I need to go back to PV equals nRT. I'm trying to solve for volume, right? So, using my algebraic skills, I'm going to solve for V. Well, what I have to do is divide by pressure. What I do to one side of the equation, I have to do to the other. So pressure over pressure cancels. I'm going to get the volume is equal to the number of moles times the gas constant times the temperature all over the pressure. So I have my equation that I need to do my calculations. Now all I need to do is plug in my values. So I'm going to extend the page down here, okay? And I know that my volume is equal to the number of moles, 7.7 moles, times the gas constant, 0.0821, and let's see, that was liters, atmospheres, over Kelvin mole, times it by my temperature, which was 329.15 Kelvin. And I'm going to divide all of that by my P, my pressure, which was 0.09 atmospheres. Now, when I look at this and I start canceling, here's a mole up top, here's a mole at the bottom. Here's a Kelvin up top, here's a Kelvin at bottom. Here's an atmosphere on top, here's an atmosphere on the bottom. So it leaves me with a value with a label of L. Is volume in L? Yeah. So I've set this up pretty good. So now my volume is equal. I'm going to go through and do my calculations. And when I did my calculations with this, I came up with a value of this, okay, 2,311.99 liters. Now, how many significant figures, I go back up to my problem, how many sig figs do I need here? Well, how many do I have right here, Cody? How many do I have right there? How many do I have right there? 1. Okay, I've got 2 placeholder zeros, and I've got the 9 there. So I have 1 sig fig. So I need to take this to 1 sig fig. So there's my 1 sig fig. My volume is going to be 2,000 liters because that 3 does not round up. I have 3 placeholder zeros there. So what I do is I collect my data, I manipulate my ideal gas law equation, and then I plug in my numbers. Kind of long problem, but I don't think it's that tough. Okay. Here's our second example. Go ahead and write that down and then copy this. We'll work it. The question states if I have an unknown quantity of a gas at a pressure of 121.6 kilopascals and a volume of 31 liters, temperatures 87 degrees Celsius, how many moles of gas do I have? Well, I collect my data. I see that I have kilopascals, so right there is my R. I'm going to use the 8.31. Okay. I have temperature in Celsius, so I'm going to have to convert that too. But once again, I just line up. I line up my PV equals nRT. I need to calculate how many moles. So my N is my unknown. So I should have everything else. Pressure is 121.6 kilopascals. Volume is 31 liters. Pressure is 121 point, wait. That's not P. What am I doing here? That's a R. R is the 8.31. 8.31 liters times kilopascals all over Kelvin times mole. My temperature is 87 degrees Celsius. I need to add the 273.15, and I get my value to be, 360.15 Kelvin. So I've collected all of my data. I need to manipulate my equation. PV equals nRT. What am I trying to solve for? Moles, which is N. So I'm going to divide RT by both sides. This side cancels, so my number of moles is going to be equal to my pressure times my volume divided by my gas constant times the temperature. So as I come down, now it's time to plug my numbers in. So my number of moles are going to equal my pressure, which was 121.6 kilopascals. Multiply that by my volume, which was 31 liters. Divide that by my gas constant, 8.31 liters times kilopascals, all over Kelvin times mole. Multiply that by the temperature, 360.15 Kelvin. So I go through and look. Kilopascals on top and bottom cancel. Top and bottom cancel right there. I have a Kelvin cancel right there. So, and this I'm sure is not a mathematical term, okay? But when I have something that is in the denominator of a denominator, it's like being on the top, okay? So the denominator of a denominator is like being on the top in the numerator. I don't know what they call that in math. Doesn't really matter to me, okay? So my N is going to be equal, I'm going to multiply 121, okay? 0.6 times 31 and divide. I can put this in my calculator in parentheses and I will divide that out to make sure my order of operations is good. And I came up with a value of 1.260 moles. Now, once again, I'm going to go back to my original problem, okay? And I'm going to look, and I see I have 2 sig figs there. I have 2 sig figs there. I have 4 sig figs there. I don't use this because that is an actual number. So I'm going to go with 2 sig figs for my answer. So when I come back down here, my number of moles are going to be 1.3. Label it moles. There's my final answer. So once again, the problem's a little bit lengthy, but it's not terribly challenging. Probably the toughest part is manipulating my gas law equation to get the correct values. Now, my next example is using my second equation. So go ahead and copy this example, and then we'll work the equation. Now, with this particular equation, I'm using PM equals DRT. Postmortem equals dirt. Okay? M is the molar mass, D is the density. We know P is pressure, R is the gas constant, T is the temperature in Kelvin. So, I'm asking the question, what is the density of a gas with the molar mass of 100 grams per mole at 5 atmospheres of pressure and 27 degrees Celsius? So I need to go through once again, and I'm going to get my setup. Only thing is now, I'm not using PV, I'm using PM, D, R, T. So I've got my different equation. I'm trying to find the density, so D is my unknown. My pressure is 0.5 atmospheres. My molar mass, my M, is 100 grams per mole. My R, well, since my pressure was in atmospheres, my constant's going to be the 0.821 liters atmospheres over Kelvin temperature. My temperature is going to be 27 degrees Celsius plus 273.15. And that's going to give me a value of 300.15 Kelvin. So now I've collected, once again, I've collected the data that I need. The only thing now is, my equation is PM equals dRT. I'm trying to solve for density, so I'm going to divide both sides by RT. Those cancel, so my density is equal to PM over RT. D is equal to P, which was 0.5 atmospheres. M was 100 grams per mole. All over. My constant times my temperature when I do my canceling, that cancels. My Kelvin cancels. My moles cancel. So it's going to leave me grams over liters. Is that a density? Absolutely. Okay? And I'm hurrying to get this done because I want you to get your homework. When I do my math, it comes out to 2.09 at 1 sig fig 2 grams per liter. Now, your homework assignment, ladies and gentlemen, is this problem right here. So go ahead and copy that, and that is your homework for tonight.